terms of a geometric sequence. So we know that there's a common ratio, we know that they're multiple together. So A, we'll find the value of R, we'll do U2 divided by U1. Oh god, that's only what it says. 1.6 divided by 64 is 2.5. So R is 2.5. B, find the value of S6. So we're using formula booklet. It's a geometric sequence, so we're using the sum formula. Right, we've got a value of 2.5, so I'm going to use this version of it because R is greater than 1. So we know that U1 is 0.64. We know that R is 2.5 to the power 6, then is 6 minus 1 over 2.5, take away 1. You can use either format, both will be the correct answer, but it's just easier to use this one because R is greater than 1. Stick that in the calc. So I'm going to do it as a fraction, so I've got my division correct. So I've got 0.64 bracket 2.5 to the power 6, take away 1, close bracket, and on the bottom 2.5, take away 1. So it's 103.74. Okay, C, find the least value of n such that the sum is greater than 75,000. So this time n is going to be, we don't know the value of n here, so we're going to have 0.64 bracket 2.5 to the n minus 1 over r, oh no, still 2.5, take away 1. So 0.64, 2.5 the n take, oops, over 1.5. So that's my expression for the sum of n terms. So that I'm going to find out when it does equal 75,000. Okay, lots of different options here. None are better than the others. You can just multiply, so you can have 0.64 2.5 to the n minus 1 equals 75,000 times 1.5. Then you can divide by 0.64, so this stuff divided by 0.64. Then you can add 1, so 2.5 to the n equals all of this plus 1, and then you can take logs of both sides. It doesn't matter, log or ln. 2.5 to n equals log of all of this, and so n is log of that stuff divided by log of 2.5. So that's going to give you an actual value of n. You could have used the graphing package, so you can plot it. So you can have alpha y equals, so we've got 0.64 brackets 2.5 to the power n minus 1 close brackets over 1.5. You can then put 75,000 as your other one, and you can graph it. Now obviously my scale here is going to go out the window, so I need to change that. It's really obviously trying to... So I need my scale here to go up to 75,500, and we're going to go up in 500. I'm going to change my x. It's going to be 0 to 20, say. Okay, and then we're going to calculate the intercept, so 5. So enter, enter, enter. So it tells us it's at 13.1803. You would have got the same answer if you'd used this method here, and there are other ways of doing it, but whatever happens, we need n as being 13.1. Now, our value has to be greater than 75,000, and n obviously has to be a whole number. So if it was 13, it wouldn't be enough. So our value of n has to be 14. So C and D are independent events. Okay, so this might come in useful here. Okay, so we want an expression in terms of k for C intersect D. So for C intersect D, we're looking at this, we would be multiplying those two values. So C intersect D would be 2k multiplied by 3k squared, which is 6k cubed. And right down, given that C intersects D is 0.162, find k. So we can say that 6k cubed equals 0.162. So we're going to put that. 0.162 divided by 6 is 0.027, so k cubed equals 0.027, and k is going to be the cube root of that. So 4, which is 0.3. Part C. So we're looking at conditional probability. So we're finding C dash given at D. So remember, this is our conditional probability formula. So if we were to rearrange this, we've got P given A. It would be P A intersect B over P A. So that would be our rearrangement. In our case, we've got P C dash D, so we would have P C dash intersect D over P D. So we need to find the not C intersecting D, so that would be not C would be 1 minus 2k, hopefully you're right at that. So not C would be this. Intersecting with this, we would multiply these two expressions together. So it's 1 minus 2k brackets 3k squared over 3k squared. So we've got 1 minus 0.6 times by 3 times 0.3 squared over 3 times 0.3 squared. Okay, so will they cancel? So you got 1 minus 0.6, that's 0.4.